Okay, this is question number 3 from the 2012 AP Physics B exam, and it is a fluid physics problem. We have a glass tube, a U-tube, with a uniform diameter, and we want to know the density of the oil. So as shown above, we've got a column of water balancing out that column of oil at various different heights. And we know there's mercury below it that's at uniform level. And first, we want to start and we want to calculate the density of the oil. So what you got to understand, the reason why there's different heights of the fluid is basically the pressure on this left side needs to equal the pressure on the right side. And because of the different densities of the fluid, you're going to have a different quantity of fluid such that it has the same pressure. And so if we are being very careful, the pressure on the left side is the atmospheric pressure, because it's open, plus the pressure of the fluid itself, which is rho GH, and it's on the left side, that fluid is oil. I don't need to worry about the mercury because I'm going to treat this dashed line as the bottom point. And so then that equals the pressure on the right side. Well, the right side's also open the atmosphere, so there's P atmosphere here. And then it's going to be plus the rho GH of the water. The atmospheric pressures cancel each other out. The G's cancel each other out. And so the density of the oil will be the density of the water times the height of the water divided by the height of the oil. And so the density of water was given as 1,000 kilograms per cubic meter. Oops. It's ugly, it's per cubic meter. And then we've got the height of the water, which is 24.5 centimeters. And we can actually leave it in centimeters because I'm going to be dividing by centimeters, and those centimeters will cancel each other. And so the height of the oil is going to be 27.2 centimeters. And so then the centimeters cancel each other out, like I already said. And I'm going to go ahead and type it in. "900 kilograms per cubic meter." That is the answer to A, and that'll be worth 3 points. We now want to calculate the absolute pressure at B, which is the interface between the water and the mercury. So we want to look at the pressure right here. To do that, I can ignore the oil now, because really that pressure is going to exist due to the atmosphere above the tube and then the fluid of the water above that spot. So for part B, we're looking at the absolute pressure, or P total, to equaling the atmosphere pressure plus the rho GH of the water. I'm going to use 100,000 pascals for atmospheric pressure, plus the quantity of rho GH of the water. I'm going to use 10 for the acceleration due to gravity. And the height of the water, in this case, we do need to convert that to meters. There's no other distance value that's going to cancel it out, so it's 0.245 meters. And so that's a total pressure of 102,450 pascal. Part B here was worth a total of 2 points. Okay, now on the left side we're going to replace that with basically a cone or a funnel, and we're going to fill it with the same volume of mercury as we did above. And the mercury therefore ends up filling the same height in the tube down below. We're going to pour the same volume of oil in and the same volume of water in. And now we want to know what is the new position of B relative to A. Now if you recall, this is point A before, and this would have been point B before, spot B. So we want to know, is B going to be below A, or is it going to be above A? And the only way to really address that is by thinking about what's true about the pressure on the left side. Because remember, before, the pressure on the left had to equal the pressure on the right, and that pressure came from the quantity of the fluid above it. Recognize from your equation, P equaling rho GH, that it's height that affects the pressure of the fluid, not volume. So, because we're using equal volume, that oil will not rise to the same height. As a result, it's not pushing down with as much pressure. And continuing that thought then, if it's not pushing down with as much pressure, that means the mercury will not be pushing up on the water with as much pressure. As a result, that bottom line, that dashed line for the water, will actually go below A. So now the mercury itself actually would probably be like this instead. So, a new position B relative to A is indeed below A. And you can justify it. I would incorporate that equation, talk about the relationship of height, talk about how you know the volume of the oil means if the volume is the same, it means the height of the oil has got to be less, etc. I'll let you word it. C was worth a total of 3 points. You're only going to get 1 point for saying below A. You're going to get those other 2 points for discussing how the height of the oil is lower, and etc. So try to be careful on how you go ahead and justify it. And then part D, we're going to go ahead and take a piece of wood and place it on the left side inside the fluid. We know its density is less than oil, and so it's going to be floating over here on the left. And we want to know what happens to the pressure at the bottom of the tube. Will it go up or down or the same? And don't overthink this one. There's no justifying that you need. It actually increases. And that's because there's more mass pushing down. So there's going to be a larger pressure on this left side. And D was worth only only 1 point. And so if you add it all up, that's actually only a total of 9 points. And so that 10th point comes from making sure there are no errors in your units over in part A and B. So if you forgot a unit up here, you would have lost that 10th point.